Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review the one-sample t-test that's used when comparing the central tendency of a continuous value to a standard like a target or a goal. I'll spend the first part of this lesson reviewing some of the critical concepts that can help you to understand how to use this test. But despite that, I do recommend that you at least try to review the prior lessons on hypothesis testing if you haven't already done so. But for now, let's review again why we even need hypothesis testing.
Well, we need hypothesis testing because, remember, our goal for the project is to resolve the problem by first building a transfer function. We don't want to just alleviate the symptoms that we're seeing, but we want to get to the root cause. You may recall my example of my daughter Hannah. We don't want to just alleviate the arthritis pain that she was feeling in her leg, but we want to heal the root cause, which was the strep throat. So if we don't know what the root cause is, then that means we need to build a transfer function to figure that out. By building the transfer function, we can know what changes, that is, what improvements that we need to make that should fix that root cause. Now, if you recall, the transfer function is defined as y equals f of x. That is, the output response of y is a function of one or more input x's. It's part of the IPO flow model, again, that we described before in the IPO flow model, where we have an input that leads to a process and an output. Well, the y refers to that output. The process piece refers to the function that's applied to an x, the x being the inputs that are part of it. So it's really expressed in the IPO flow model to an equation. Now, how does this transfer function fit with hypothesis testing? Well, hypothesis testing tells us which of those x's, which of those inputs that we're looking at, are independently influencing the y, the output metric. When we reject a null hypothesis, we're building evidence proving which x's are guilty of driving the y. And what we'll do at the end is we'll compile all the evidence in the improve phase of DMAIC, and that's when we'll begin to fix those root causes or come up with a plan that's going to fix those root causes. Now that we know from the hypothesis testing which of the x's are the most critical x's that have the most influence and where we need to make the biggest changes that are going to affect our output y.
Okay, now let's review again the various steps that we follow when doing hypothesis testing.
On a high level, the steps begin with a four-step process, which was starting with a practical problem. We're stating the problem as a yes or no question, and then we want to convert that problem into a statistical problem. That's going to help us to figure out which is the right statistical tool or method we're going to use to help figure out how we're going to do the analysis. And then we apply that statistical tool or concept on it, and then we interpret the results from that and come up with some analytical answer. And then from that, we would interpret the analytical answer into some practical solution or some practical way in applying that so it makes sense to us. And at the heart of doing the hypothesis testing, again, for steps 2 or 3, that's where we drill down to 6 additional sub-processes or sub-steps in order to figure that out. So it started off with defining the objective. Then we want to state the null and the alternative hypotheses. Then we define the confidence level and the power levels based off of the alpha and beta risks that were identified. Collect the sample data, and we want to calculate the p-value. All these are part of building this statistical problem. And then once we've done that and run the test, then we interpret the results. This is going to be the point where we decide whether we're going to accept or reject the null hypothesis. This is what we'd follow when we want to go through the formal hypothesis testing.
All right, now let's review again the chart for finding the right statistical test and where the one-sample t-test fits into all this.
As we try to use this drill down again to figure out what's the right statistical test for us to use, this is the test we're going to be looking at, the one-sample t-test. By falling into this group, this is because we have one value that we're looking at, like the primary output y is a continuous value plus some other x, which is a discrete value, and what we're measuring is central tendency. That is like looking at the mean or the median. That central tendency metric. And we would answer in this case here, is the data normal? Yes. So we would follow down this path here, and right now we're going to be using the comparison of 1 to a standard. So again, that's where we fall into this test, where we select the one sample t-test that we're reviewing in this lesson.
Now let's review again the concept of confidence intervals, which is essential for understanding statistical tests like this.
We have to remember the confidence intervals are an estimated upper and lower range of the mean. So the confidence interval will change or become more narrow when you add more samples. So example we've given before is when we have fewer samples, the population mean falls somewhere within this wide interval. But as we get more samples and distribution grows, the confidence interval represented by these dashed lines gets more narrow. So as we get more and more data that increases, then the confidence interval gets more and more narrow because we could be more confident having more data where the population mean should fall. So we've got to remember that statistics are intended to help us make inferences about a population. So let's say we have a mean of 57 with a 95% confidence interval that falls from 55 to 59. Well, that would imply that although the sample mean is only 57, then we can have 95% confidence the population mean will fall somewhere between 55 and 59. So the more data that we collect, the more narrow this interval becomes. So if we were to double our sample size or triple our sample size, then the confidence interval might narrow. Again, we might come up with the same mean of 57, but it might make it more narrow where now the range is between 56 and 58. So it gets more and more narrow with the more data that we collect. So the first step that we have in hypothesis testing is to define the objective by asking, is there a difference between something or whatever it is that we're comparing? Now, the statistical test generally will compare the different confidence intervals between factors to see if that difference actually exists. So an example we've given before is, let's say we only have 20 samples we pulled and we're looking at the difference between factor A and factor B. We might have a mean here at this value for factor A and a mean represented by the dot here for factor B. And the line spread out across each one here between each factor represents the confidence interval. So for factor A, the average actually falls just above 3, maybe like a 3.05 or something like that. And the confidence interval here shows that the population mean actually could fall as low as maybe 2.7, or it could be as high as, in this case, maybe like a 3.3, somewhere within this range, even though the dot represents this is where the mean falls. Well, for factor B, this mean falls at this dot, and that means the population mean can fall somewhere within this range. So you got to remember the tests look for the overlap between the confidence intervals. If there's a lot of overlap between them, then there's a good chance that the actual population mean between the compared factors are possibly the same or very close to being the same, which is going to result in a higher p-value, a higher level of risk before we can claim any difference. Well, the more samples we collect, then there's going to be more narrow confidence intervals. Having more narrow confidence intervals means there's less of an overlap between them. So that means there's a lot less chance that the population mean is going to fall within the same more narrow spot between both of these compared factors. And as you continue to collect even more data, then as shown here, there's no overlap. And if that becomes the case, then we would say that there is a low or no p-value where we can conclude, yes, there is a statistical difference between these factors after all.
Now let's dive into describing the one sample t-test and how to run it in MiniTab.
Well, when is it that you should use the one sample t-test? Well, that's when we want to compare one mean or average value with a standard or some sort of target or goal that's being set. Now, how do you find this in MiniTab? You're going to go to the Stat menu, select Basic Statistics, and choose the one sample t option. And then what are the inputs for the test itself? Well, when you select that option, it's going to open up this dialog box for you. And what you're going to do is you're going to select whatever sample that you want to use, the column that includes the sample that you're going to be looking at, that represents the continuous data that you want to be able to test. And then you're also going to select down here that standard or target that you're going to be comparing those values to. Now you can also choose the options button here. By selecting that, you're going to open up this new dialog box, and this is where you can define the confidence level, and it's where you can also define the alternative value depending on how you defined your null and alternative hypotheses.
Now let's see how this test works when we apply it in an example.
Well, in this example, we'll look at MetricA, and MetricA is basically an arbitrary set of values in the column called MetricA in the sample data file that's provided in this website. So for the practical problem, we'll ask ourselves, does the mean or the average of MetricA exceed the target of 500? Well, for the statistical problem, again, we're going to state the null and alternative hypotheses, where we'll say the null hypothesis is where the mean, represented by the mu, is less than or equal to 500. Otherwise, the alternative is that the mean is greater than 500. So what do we mean by this? We're saying that if the goal is actually met, we meet the goal of exceeding the target of 500, then we expect that we're going to be rejecting this null hypothesis and that we're going to accept the alternative hypothesis, which proves that we met the goal. And this is how we'd normally interpret this based off of how we define the null and alternative hypothesis. But we can, if we change the values on this where the null is greater than or equal to 500 and the alternative is less than, then we would just have the reverse that we would expect. It doesn't matter which way you really represent it, as long as you understand how you're representing it and that you set up your test appropriately to what you represent here. So for the confidence and power levels, we'll use the default of 95% for confidence level. And for inputting it into MiniTab, we're going to go to the Stat menu, select Basic Statistics, and choose the One Sample T option. Then we're going to select the Samples and Columns section and select MetricA from the list of columns. And then we're going to check the box that says to perform the hypothesis test, and we're going to type in our goal of 500. We'll also click the Options button, and then we're going to make sure that we have 95% represented as our confidence level, and that for the alternative we're going to choose greater than, just like we defined up here earlier. So for the solution, we're going to look at the results that come out in the session window within MiniTab, and as usual we're going to be looking at the p-value. Now in this case the p-value comes out at 0.177. That 177 is 17 or almost 18%. That is greater than our alpha risk that we're willing to accept. So in this case, we failed to reject the null hypothesis. That is, we're going to accept the null hypothesis that the average is actually less than or equal to 500. Now, one of the things you could look at on here is the 95% lower bound is like our confidence interval. So when we see that the lower bound is 483, what that essentially means is that the lower bound of our confidence interval dips below our 500 target. And because it dips below it, and it dips it as far down as 483 for a confidence interval, then the chances are great that the actual population mean could fall, or at least there's a 17 or almost 18% chance the population mean could fall below 500, somewhere between 483 as our lower bound and 500 of our target. So from a practical standpoint, we'd say this sample that we're using on here is insufficient to prove that MetricA actually exceeds our target of 500. Now, why did something like this happen, and how can we change the results? Well, it's essentially because we probably only have 100 samples. If we were to increase our sample size, then by increasing our sample size, we're going to make our confidence interval more narrow. So if we had doubled our sample size or tripled our sample size, then let's say we have the same exact results as before, whereas we're coming to the same exact mean of 521. Well, because we've increased our sample size, it's going to shrink or make more narrow or decrease our confidence interval. And because our confidence interval now, with only having 100 records, dips down to 483, by doubling or tripling our sample size, that would make this actually as a lower bound get higher, which means it's making that confidence interval more narrow. And as a result, the higher this gets, the higher that is closer to 500, then we're probably going to see less of a chance that your actual population mean is going to fall below 500. So you're probably going to see this p-value dipping lower and lower. Now that's assuming that the results, if we were to double or triple the sample, were exactly what we're seeing for the 100 samples that we're seeing right now. That's what we would see. This lower the bound is actually going to increase, and the p-value is probably going to be decreasing. However, if you're normally running this, you probably would get different results if you were to double or triple your sample size. So again, for this sake, we're assuming that we'd have the same exact results, and that's what we'd expect to see in the difference here. But in a real situation, you're probably going to end up getting very different results. And again, we'd have to take into consideration the confidence interval for those different results and the p-value based off of those different results.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
I'd like you to refer back to the output Y and those different input X's that you identified while we're doing this hypothesis testing. And for any of those factors where you have a continuous value, try applying the one sample t-test. In order to do this, that you'll need to compare that factor with some sort of goal that you might have for that factor, or a target that's already set for the goal. So you might want to find out what that is as you run this one sample t-test. And you can use this for any other factors that you might have in your organization in order to test this exercise as well. So before you run the one sample t-test, first, based off of the raw numbers that you're looking at for that particular metric, ask yourself, does the factor meet or exceed the goal? Then run the one sample t-test, and then ask yourself, does the factor statistically meet or exceed the goal? Now, if the answers again to these last two questions are different, then how does this affect how you typically measure and communicate that factor within your organization? Again, as an example, does the factor meeting or not meeting the goal affect any financial decisions, such as how people are compensated, or process changes, such as how the process may be modified, or any other types of critical actions like that? If it does affect those, then how should the results from this one sample t-test be used to influence your organization? Should it change how those goals are set, or how each of those factors are being measured, or should it change how we react when we compare that metric to the goal?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hanson. Thanks for watching.